this computer. There we go. All right. So, somebody yell at me at 10:59 because I had previously said we didn't have class today because I didn't know when break started. It was off my calendar, and the dean scheduled this giant meeting with a bunch of people in it, including me, for 11, but at least I don't have to go far. So we finish up at 10:59, then I can switch over to that Zoom call. So I'll apologize for that, but I guess 55 minutes or 53 minutes is better than a canceled class, so we can get into binary trees some. Hopefully, me not giving you homework will allow several of you to do better on your 370 test today.
So we think.
I'm going to be checking in afterwards, expecting. I'm going to tell Dr. Locklear they didn't have 300 homework, so they can't blame it on that. Because I had a room of people that weren't willing to tell me that break didn't start when I advertised that it started. Historically, maybe I would have been traveling somewhere, but right now I don't have anything better to do. All right, so today we're
honestly, I don't even know better. So much stuff is changing right now. I thought maybe they gave us an extra day or something.
Yeah, no, I get it. I get it. If anything, I would have thought maybe they would take away a day. Although usually you don't take away stuff, it's harder to do, but you know, because typically, you know, not that they aren't religiously observed days, but Good Friday and was it Maundy Monday? Or is it Maundy Thursday? Well, whatever it is. Monday means something. So usually those are religiously observed holidays in the Christian church, but they, I think from an academic perspective, they usually just gave it to you as travel time because you're coming home from Easter or heading out to Easter. Where now we have nowhere to go. All right, so we're going to talk about nonlinear linked data structures. So up to this point, we've been talking about linear ones. So our linear linked data structures that we've looked at, kind of the traditional ones, but you can hopefully use your imagination. You can say, well, I can create all sorts of data structures off of this idea of having a bunch of things chained together in some sort of possibly interesting way. So we do want to kind of stretch our minds a little bit and consider that idea. That everything doesn't have to look exactly like a stack or exactly like a queue. You know, take Towers of Hanoi as an example. I mean, the towers were stack-based, but they behave differently than a normal stack. Same thing with Shunting Yard. Our stack for operations, it behaves differently than a traditional stack. And you can certainly have little tweaks on just even the idea of stacks and queues and those types of things. So really focus on what we've talked about up to this point as being in this group of linear linked data structures, but not necessarily that those are your only options. So linked list, stack, queue. I'm going to throw some other things in there like a heap. All right, so what is nonlinear linked data structure? Well, if linear means that at most well, linear means in a line, right? So nonlinear would mean not necessarily in a line. So in a linear linked data structure, we have at most one neighbor in the line. You know, a doubly linked list technically has two neighbors, but they're still in a line. So let's just leave it at this this idea. Okay, everybody's in a line in a linear linked data structure. In a nonlinear linked data structure, these are going to be stuff like binary trees, AVL trees, red-black trees, N-ary trees, a lot of trees, graphs. I'll leave it at that.
I have a question.
Sure.
So like a library in Python, what does that boil down to? Is it like similar to an array, to a linked list?
Which?
Like, no, like or a dictionary, sorry, in Python.
Oh, I would think a dictionary would be, well, I'm not positive how it's implemented under the hood, but I would implement it as a linked list of name value pair objects.
Okay. Thank you.
Because, and you're going to see once we get into the trees here, that the structure of a dictionary isn't important. The use of a dictionary is that you could ask for the value associated with the key and it gives you something. Where we've seen that the behavior of a stack means something to us. The behavior of a queue means something to us. How a stack and how a queue are actually implemented is unimportant to us from a using it as a tool perspective, right? We could certainly write a stack using an array. Just create a big old array and hope that you don't use too much of it. In fact, actually operating systems effectively have a stack data structure that lives in system memory that effectively is an array because they set the stack size. They say, hey, this is the amount of size you have to work with in the stack. Don't put too much on here. You know, once you get to, 50 magazines in the stack, things are going to start falling over. So they actually put a limit on it. And if you have a limit on a stack, all of a sudden you can now safely make that consideration. Why did it just switch? You can safely make that consideration. I think I just switched screens with my mind. You can safely make that consideration that I don't need to do this as a linked data structure. I can do this as a array, a contiguous fixed data structure. Because hey, I'm allowing 50 things in my stack. I just have to keep track of where the current top of the stack is, and I have to keep track of how many things are in that stack as I push and pop and peek. So you can certainly implement that off of array. So even as we talk about stacks, queues, and I don't think you could necessarily have a linked list that is implemented as an array. You could probably have something that behaves like that, but all of a sudden it's no longer a linked list. So I think linked list implies that that guy is a linear linked data structure, as opposed to an array which is stored in contiguous memory. Whereas I think if we took the idea of a tree type structure, which we're going to talk about here in a minute, that probably fits the mold of a nonlinear linked data structure. But a lot of these things you can implement in different ways. You can come up with a pretty ghetto solution to something as long as from the end user's perspective, the programmer's perspective, it behaves the way that they expected a stack or a tree or whatever to behave. They don't need to know how janky it is under the hood, at the end of the day. So from a data structures and algorithms perspective that, we're looking at this from an academic viewpoint, it's good for us to understand kind of the pros and cons of having things strewn about memory and us linked to it from a, because as a computer scientist, it's important that we wrap our mind around memory efficiency versus performance and things like that, because in our careers, we might have to solve a problem where those things are important. Even though we all realize that if you just look at your homework assignments and the things that you've programmed up to this point, 99.9% of the stuff we deal with, performance and memory isn't a problem, right? You're not going to run out of system memory. Performance, it runs just as fast if you wrote it in the worst way possible as if you wrote it in the best way possible. So most of your career is going to come from that perspective. In fact, if I just throw two things out there, I throw performance versus memory efficiency. What's the third thing that you think you might need to consider in your career?
Accuracy.
Oh, well, accuracy, we should always, so not a wrong answer, but it should always be accurate. You just get a little random code generator and boss gives you a project to do it. Like, here, this is what came out. Here you go. What else? What dynamic? Go ahead.
How much time it's going to take us to implement?
Okay, and that's actually related to what I was thinking. So certainly, if you're working for a company, and you know, boss gives you some project to do, yeah, I'm sure you can probably come up with some really fancy way or a really efficient way or of doing something, but maybe that's going to take you 10 hours where you can just kind of brute force approach it and knock it out in 45 minutes. You know, which is the boss going to appreciate more if the performance and memory behind the scenes, that's assuming that you even save performance and stuff. Maybe your solution just looks prettier. But you know, which is your boss going to appreciate more? The one that you got done in 45 minutes and he only had to pay you 45 minutes for, or the one that took you 10 hours? You know, he's going to like the 45-minute one most of the time, unless there was a great reason for you to do it the other way. If performance was a major issue, if memory efficiency was a major issue. Now, the thing I was thinking of is, especially in industry, you're likely not the only one that's going to be working on that program, or you're not the only one who is going to see your code eventually, whether that's this week or in 6 months when somebody goes to do an update or is trying to hunt down a bug somewhere or whatever. Your code needs to be readable. And if you come up with some super fancy, efficient solution to something, that might be great for a mathematician to look at and say, oh man, that's really cool what you did there with combinatorics and things like that. But at the end of the day, a normal non-PhD mathematician might look at your code and not have a clue what you're doing. So for their perspective, it would be a lot easier if your code was significantly more readable, so they understood what you were going, what you were looking at. You know, you even saw an example of this last class where, you know, I wrote into our stacks and our queues that is empty function. Now, all that thing did was wrap me asking the question of whether the count was greater than 0, right? But if somebody's reading through your code and they see you asking the question, is the stack empty? That's very meaningful at a glance. Where is the stack's count greater than 0? Most programmers are going to pretty quickly translate that, but you know, that does require a little bit of thought to translate it. So I would say, you know, a very, very, very high percentage of the time in industry, writing code that your coworkers are going to be able to follow is probably the most important thing after accuracy, you know, as Noah pointed out. So obviously your code should work. But most of the time, making sure other people can follow your code so they can manage it later on is most important. And only sometimes is a problem going to lend itself to, or is going to demand that it has to be very fast or very memory efficient, something like that. All right, that makes some sense? Okay, so these are things that go into industry, and there's not always, the most elegant way isn't always the best way. In fact, most of the time, the most readable way is the best way, even if you tacked on an extra 30 lines of code. Okay, so what do trees look like? Sorry about that. I don't know if you can see that the thing dropped. Oh, somebody's chatting. Oh, golden nuggets of wisdom. It is. All right. And it really is an important point. You know, I would say, you know, not to harp on it too much longer, but just one more thing. If some of you ask yourselves, in fact, you know, I think we'll throw Noah under the bus. Noah's very inquisitive. He likes to learn about all sorts of things beyond what he might be looking at right now. And I think that's usually very good because he's looking at it from an academic perspective. He wants to learn all these things. But if you've noticed the last couple of classes, he's asked questions like, oh, could I use recursion for this? Or could I do this, that, and the next thing for this? I think sometimes when you go into a project and you immediately try to start solving it in some complex way, that's usually the wrong way of going about it. I would say whenever you start a project, think about what is the most straightforward way I can solve this, and then solve it that way. And then step back and ask yourself, is this going to be a problem? Is speed something that needs to be considered? Is memory footprint something that needs to be considered? Is somebody else going to be able to read this? Most likely, if you went through a straightforward approach to it, somebody else would be able to read it at least better than your weird way you might try to solve it. The weird way is great for, you know, when you're academically learning this, you're going to say, hey, look, I'm going to handcuff myself for this project and I'm only allowed to solve it recursively. So that's just my constraint. And you think about, since 200, I've given you constraints where you're not allowed to use certain things for assignments. We all know there's libraries out there. If you're going and Google searching and you're seeing some stuff that, you know, would have taken, you know, shaved hours off your homework because you could just use some tool that's already out there, that's great. When you're in industry, do that. As long as the tool is part of the normal library, you're not having to bring in some third-party possible buggy type thing. But you know, when you have constraints, a lot of learning can take place in that because you're having to kind of work with one hand tied behind your back. But once you're in industry and it's a matter of somebody's paying you for your time and you want to have throughput, and also your coworkers who might be at all sorts of different skill levels. You know, that's another thing you look at. I mean, just like in class, you know, when you work with folks on in your study groups, you're going to have several different skill levels in there. And that's kind of the purpose of those study groups, right? You have the kind of the person who's maybe leading the group and they're the strong programmer, and the other people are the aspiring programmers that maybe understand stuff from a student's perspective, maybe better than from when I explain it, or maybe I'm going too fast or something like that. So that's very constructive from an academic perspective. But now when you translate that into industry, sure, you should be able to make the assumption that everybody in industry should be capable of doing their job, but you're still going to have different performance levels, right? You know, a basketball team's still going to have their Michael Jordan, and then they're still going to have their support group. And every single one of them is important, and knowing what each one kind of is capable of doing and where they shine is also important. Because that person who maybe can't solve the hardest problems, but maybe is very efficient or tedious or you know, whatever, can do like the grunt work, the stuff that, like, for instance, when I'm writing software in Teams, I don't do it as much anymore, but when I did do it, hopefully you've gathered that I'm pretty decent at programming. So I was typically that Jordan type guy on the team. But what that translated to is some weaknesses. And that weakness is if something was boring, if something was kind of beneath me, where I knew I could just throw 4 hours at that, it would be done, I didn't want to do it. And that's a problem. I could do it, but I didn't want to do it. You might have somebody else on the team where that's their contribution. They can just do that all day long and write it very, you know, solidly and things like that. All those people go together and make up a successful team. And you want to make sure that the code you write is understandable by that person who, you know, is your grunt worker, who's just as important as your all-star, because they're they're doing something and maybe other people don't necessarily want to do, but it's the job that still needs to get done. But they need to be able to follow your code, to integrate it, things like that. So always think about it from that perspective first. Your bosses and your raises will appreciate you later. Okay, so let's look at what a tree looks like, and I'm just going to kind of build out a generic tree here, and then we'll fix it. Or then we'll modify from it. Spread these guys out a little bit. I'm not going to go too many layers down. So one thing we're going to find pretty quick is trees are a little bit difficult to represent when you go to print them out if you can't do it visually. So we're going to mostly do it linearly when we show our trees. call that good enough. Here, I'm just going to put random numbers in here. We'll leave that as a 3. All right, so if you wanted to draw some lines here to kind of see how these guys connect, you know, we have this guy going here, this guy going here. That guy going there, and then imagine the lines to all the other ones. All right, so this is kind of the top of the tree. Actually, trees, usually when we think about trees in data structures, they're actually upside down. So this is the root of the tree. All right, so the base of the tree. And from that, we grow up. So we have, in this case, 3 branches coming off of that guy. This guy has 3 branches coming off of him. This guy has 1 branch coming off of him. This guy has 1 branch. This guy has 1 branch. And all these bottom ones have no branches. So let's give a little definition to some of these things. So we'll call this parts of a tree. So we have the root. This is the top, what we might say, base of the tree. So depending on how you like to mentally visualize a tree, you can either visualize it as an upside down tree where the top of it is the guy at the very top, and that's going to be a single node for a tree. Or you could think of it like you look at a tree in nature, you have the trunk, and then everything branches off from the trunk. So the root would be our trunk portion of the tree, the bottom of the tree. All right. Then we also have leaves or leaves. These are, well, I'm going to call them nodes since we're programmers here. These are nodes that have no children. And then a child, these are nodes that have at least 1 child. Now I'm going to throw a little interesting fact here. We're not going to end up seeing this in code for a little bit, but it's a fact nonetheless. So just something to kind of keep in mind for right now. A child node is actually the root of a subtree. So if I go back here, we have this giant tree here in which 3 up here is the root node. But isn't it true that 7 here is the root node of this subtree? And 13 here is the root node of this subtree? And 90 is the root node of this subtree? And 111 is, we can roughly say it's the root node of this really boring tree, but as I've written it, it's only child nodes. So we wouldn't call this guy a tree. He's been cut down. He's no longer a tree. But hopefully we see that a tree, let's just give myself a slide here in the middle. Now, first of all, very rarely would you implement something that's just a generic tree. Usually a tree is going to have some rules associated with it so that it has meaning for how you're going to solve it. Just like stacks have the push pop peak rule. Everything gets added to the top, everything gets removed from the top. So we've applied rules to a structure that kind of dictates how we're going to use it. All right, so a tree data structure is a collection of subtrees. All right, and that's going to help us as we start writing these. And this, you'll like this, Noah, because this is going to lend itself to what I call pseudo recursion. That is, when a node calls the same function it is currently in, but on a different node. So instead of, recursion is when a function calls itself from within itself. In this case, a node might be in the middle of its do something function. And instead of him calling his own do something function again, he actually calls another node's do something function. So it's the same function, just not the one owned by that guy. So I like to call that pseudo recursion. And we'll see examples of that, but just throwing a couple of highlights out there since we're not going to dive into code too much until right after break. Okay. So this is what a generic tree might look like. That's the structure of it. And I think we can all agree pretty quickly, this is not linear, right? We got things that are connected to a whole bunch of other things. If we turn this into a graph, then what you could have is you could have like 17 hooked to the 5. So think of a graph like a map. If you're looking at a map of Wisconsin, you're going to have all these different towns. Those are nodes on the map. And you have all sorts of different roads going between those towns, and multiple roads go into some towns and multiple roads go into other towns, and there's some overlap. So you might have a way of getting to Milwaukee. So here, maybe this is Green Bay. So we have Green Bay, then we have Mequon, then we have Milwaukee, something like that. It'd be a little bit more linear. But then from Milwaukee, I can actually go farther. I could go up the tree. So maybe this guy here is like Menominee Falls, something like that. Brown deer. So I could actually hop from this branch of the tree over to this other branch, and now this guy becomes a graph when you're no longer following the tree structure of it. So when we get to graphs, we're going to think about them as maps. So we're going to actually solve a famous problem called the traveling salesman problem, TSP.
I have a question, by the way.
Go ahead.
When I look at the picture, so the 3 is the root, right? So like I'm trying to understand the sort of paths of the tree. So what did you say was considered the child in this case?
7, 5, and 13 are children of 3.
Oh, okay, so that's a type. And then are they also considered leaves too?
5 is a leaf because he has no children.
Oh, right.
7 has children, so he's not a leaf.
Oh, okay.
So 7 has 3 children, 3, 2, and 17. 17's a leaf, 2 is a leaf. So if you want to color code these guys.
Yeah, I see it.
Would 7 and 13 be considered the child's then?
Well, 5 is a child of 3, but 5, he is a leaf node as well.
Okay,
so 5 is a child of 3, but he is a leaf node in that he has no children.
Yeah, I get it.
Okay. So we look at this tree, and there's really no rhyme or reason to why things are in this tree in a certain way. Instead, what we have is this idea of a tree structure, where nodes have a list of child nodes. Some trees are going to have a finite list. Other trees, like I mentioned up here, n-ary trees. N-ary trees can have any number of children. So if I was giving a definition to what I'm looking at here, this is an n-ary tree. So the top level has 3 children. This has 3 children. This guy has 1 child. So I suppose by the way I've written it right now, we could call this guy a trinary tree because I don't have any more than 3 children anywhere, but I could put a 4th child somewhere in here and be perfectly fine. Then we can call it an n-ary tree since we haven't really dictated any rules. But those things are relatively unimportant in data structures because only binary trees, as you might imagine, something at the power of 2, is gives us structure. After that, we're more taking advantage of the tree archetype, if you will, for solving interesting problems that kind of need us to separate things out. And when we get to that, I'll show you some examples. But right now, we're going to look at this guy and say, there's really no rhyme or reason to this data right now. It looks nice. It's, you know, it looks like a tree. This sounds looks really complex or whatever. But this hasn't helped us at all. These numbers are just strewn about inside here. You know, I have numbers all over the place that, you know, why is a 17 here versus over here or something like that. There's no rhyme or reason currently. All right, so we'll just throw a little label on this guy for right now. Not a useful tree in that it doesn't have rules as to where things are. Still a tree, still looks pretty, still looks like you know what you're doing. You know, if you need filler for something you're turning into a boss for a report or something, just draw a complex looking tree on there and just call it like figure, you know, 14A. Never refer to it, just looks like you did some extra work. Don't do that, by the way, but just it'd be funny. All right, so I'm going to actually steal this slide, and we're going to move all my toys over here for a second. All right, so we're going to talk about binary trees. So a binary tree, each node has at most 2 child nodes. That's one rule of a binary tree. We can never have more than 2 child nodes. We can have 0, 1, or 2. 0, 1, or 2 children. All nodes to the left of a node are greater than or equal to the node itself. I'm sorry, less than or equal to the node itself. All nodes to the right of a node are greater than the node itself. These are the rules associated with binary trees. So we can't have any more than 2 children. Everything to the left of something is less than or equal to it. Everything to the right of something is greater than it. So let's look at this as an example. I'll throw in one more thing here. More than one tree with the exact same values stored will look different depending on the order in which the values were added to the tree. And you're going to see that as an example here. We're going to play a game. All right, so I'm actually going to copy this slide twice. All right, so these are our toys down here at the bottom, and we have the same toys here. All right, so pick one of my nodes here to be the root node. Which of these nodes is somebody's favorite? Just pick one.
13.
13. Where's my 13? Okay, so this is our root node. All right, so our tree starts with we had the empty tree. We added 13 to the empty tree, and because the root didn't point anywhere, we just added him. He's right there at the top. Okay, so now who are we going to put onto the tree next? Pick a number, any number. I heard 5. All right, so we're gonna add the 5. All right, So we try to add this guy onto the top of the tree. There's already something at the root. So now, is this 5 less than or equal to 13, or is he greater than 13? He's less than or equal to it. So 13 is going to try to add this 5 to his left child. And this left child is currently null, so we can go ahead and put that 5 there. All right, now let's go ahead and let's try to add the 2. So we drop the 2 onto the top of the tree. So this is kind of like, what was it, on The Price is Right? Or Let's Make a Deal. I don't remember which of the 2 shows. They had a game called Plinko, where you drop something at the top and it kind of ping pongs around until it finally gets into one of the slots in the bottom. So we drop this 2 in on the top. We don't have a home for it at the top because that place is already taken. Is a 2 less than or equal to 13, or is it greater than 13? It's less than or equal to, so we're going to try to drop this guy onto the left subtree. Is the left subtree available? It's not. So is a 2 less than or equal to 5, or is it greater than 5? It's less than or equal to. So we'll try to drop this guy onto the left subtree, and that spot's available. All right, now let's grab the 90. So we'll take the 90, drop it onto the tree, and this spot's not available. Is it less than or equal to? No. Is it greater than? Yes. So we'll try to drop it to the right subtree, and we did that. Let's see here. I'm going to spread these guys out just a little bit. All right, so we'll drop a 3 in now. So is there room here? No. 3 is less than or equal to 13, so we'll go here. Is there room here? No. 3 is less than or equal to 5. Is there room here? No. 3 is greater than 2. So he'll be the right subtree. We'll drop another 3 in. No room here, he's less than or equal to. No room here, he's less than or equal to. No room here, he's greater than or equal to. No room here, he's less than or equal to. So we'll drop him here. Now we'll do the 5. Drop this guy in here. Is 13, is this available? No, he's less than or equal to. Is this guy available? No, he's less than or equal to. Is this guy available? No, he's greater than. Is this guy available? No, he's greater than. So we'll put him right there. Now we'll drop in the 111. Is this available? No, he's greater than. Is this available? No, he's greater than. This is available. We'll drop in the 7. Is this guy available? No, he's less than or equal to. Is this guy available? No, he's greater than. We'll place him right here. Then we drop the 17. This guy available? No, he's greater than. Is this guy available? No, he's less than or equal to. So we'll drop him right there. All right, so now we have a binary tree that follows some set rules. Pick any node in this tree, and everything to the left of that node will be less than or equal to it, and everything to the right of that node will be greater than it. So notice all of these values over here are greater than 13. All of these values over here are less than or equal to 13. All of these values right here are, actually it's all these values right there. Remember I told you it's a little bit tricky to draw trees. There, we'll spread out a little bit better. So everything here is less than or equal to 5. Everything over here is less than or equal to 2. There's nothing. Everything over here is greater than 2. All right, see how trees work like this? Now, right off the bat, if I come into this next thing and I choose to have my top node be 2, and then I choose 90, and 90 is greater than 2, and I choose 5. 5 is greater than 2, but less than 90. I'm going to actually spread this way over here. Then I'll choose 3, greater than 2, less than 90, less than or equal to 5. Then I'll choose 13, greater than 2, less than or equal to 90, greater than 5. Put that guy there. Choose the 17. 17 is greater than 2, less than or equal to 90, greater than 5, greater than 13. So he'll go here. We'll drop the 7. 7 is greater than 2, less than or equal to 90, greater than 15, less than or equal to 13. We'll drop in the 3, greater than 2, less than or equal to 90, less than or equal to 5, less than or equal to 3. Drop them there. The 111, greater than. So we'll put him here. And then the 5, we have this guy use greater than 2, less than or equal to 90, less than or equal to 5, greater than 3. So he'll go right there. All right, so the exact same values that we're storing, but notice how these trees look quite different. And it's because of the order in which they were added to the tree. In fact, this is a good extreme in that there is nothing on the left-hand side of the larger tree because the smallest value is a 2. Everything over here is greater than 2. Everything here is less than or equal to 5. Everything here is greater than 5. Everything here is greater than 90. Everything here is less than or equal to 90. All right, so everybody see how we could take the identical data but get different trees from that identical data depending on the order in which it was added. All right, so now I'm going to throw something out here, and this is going to be more of an efficiency type thing. Tree balancing. And we're only going to briefly talk about tree balancing this semester. In fact, this might be, I'm sure I'll mention it again in passing as like things come up, but I'm going to make a statement here that says a tree is out of balance when one side is greater, let's say is deeper than one greater than the other side. Kind of a weird way of saying it, I guess. So in this example, the depth of the left tree, 1, 2, 3, 4. The depth of the right tree is 1, 2. So this tree is currently out of balance, just barely. Now, you could make the argument, because balancing trees is expensive. So we can say that by definition, if it's greater than one level deeper on one side than the other, this guy's 2 levels deeper. So we could definitely say this is out of balance, but it's not that far out of balance. But, so we could say that if it's 2 levels, we're gonna let it slide from a balancing perspective. But there's algorithms for what are called self-balancing trees. If we come back up here, I mentioned this idea of like an ABL tree and a red-black tree. I'll just throw on this slide. Self-balancing trees are ABL and red-black. So these are trees that operate like binary trees, like we just looked at here. But after we add something, we ask, is this tree out of balance? If it is, we rebalance it. And usually that's done through rotations. So you can imagine that this tree right here that we're looking at got out of balance pretty quickly. So you would have kind of thought about like taking the tree and kind of turning it. Where we would have rotated this 2, it would have dropped down here, and the 90 would have become the new top level node, for instance. And then if it got out of balance again, we maybe would have rotated it one way or the other to kind of keep it within one level of each side. And what that then produces for us is a tree you know, at a glance, even though we saw technically this tree is out of balance right now, but at a glance, a much more balanced tree. This looks like a reasonable tree. This guy doesn't look so much like a tree. Okay, this looks like one of those trees by the highway where they've cut off one half of it to make sure that the thing's not hanging over the highway. So it no longer really looks like a tree. Okay. So tree balancing, we know a tree is out of balance if one side's deeper than another. We have specific self-balancing tree algorithms that attempt to keep a tree in balance. Advantage of a balanced tree is that it is quicker to search. Now, I promise you that if we wrote a program to search this tree, we wrote a program to search this tree for a value, to a human being, they're going to feel the same. One's not going to feel faster or slower than the other one. We're going to zip right through these tiny trees. But as you might imagine, in a very, very, very large database, so databases are often built out of tree data structures. So that's an applied aspect of trees. If you have tons and tons and tons and tons of nodes in your tree, and that tree gets very out of balance, like we have on this one has a depth of 0 on one side and a depth of 1, 2, 3, 4 on the other side. It is very out of balance. And because of that, and we could have actually made it even more out of balance if we would have added these things in a worse order, let's say. But if we were searching this tree, we would basically, we're asking a question up here, and unless we get lucky, we're still dealing with almost all of our data the second time we look. So if we're searching for a value, let's say we're searching for a 13 in here. We say, is this a 13? No, it's not. Well, should a 13 come to the left of it or to the right of it? Well, it should come to the right. It's greater. So we'll check that tree. Is this a 13? No, it's not. Now, keep in mind, if this was a balanced tree, as soon as we found out that this guy was not the value we were searching for, we could have cut out half of the things I was going to search through. If this was a balanced tree, if I was looking at something like this and I was searching for 17, I checked, is this 17? And the answer is no. Should a 17 come to the left or to the right of it? As soon as I say it comes to the right of it, all these values there are now out of the equation, right? We'll never have to look at them for this one. So we more than cut the amount of data we're searching in half. So you see how that's a lot more efficient? By having a balanced tree and having the tree stored in a certain order. Sometimes these are called phone book searches, or it's called a binary search.
If there was a node that you wanted to access like a lot, would it then be advantageous to purposely make it unbalanced because you know you're going to be accessing that one node very frequently?
I would say at that point, maybe a binary tree is not the right thing, because at that point you have like prior knowledge. You know, like you kind of know that you're going to be accessing that node often, which is I don't know how helpful that is, I guess. So I suppose if you had some sort of anomaly in your data set where you just had this one dude that, you know, let's say it was a bank or something like that. You had this giant investor in the bank, but he wasn't didn't have the most money in the bank, but he had a lot of money, but he was very active. You know, I suppose you could kind of have like an extra program that held a pointer to that guy, so you can kind of quickly access that guy's file without searching through it. Something like that. I mean, you can probably make an argument for that being the right tool for the job. But in general, we don't really know much about this data. Clancy is raising his hand.
Yeah, I just want to remind you, it's 10:59.
All right, I appreciate it.
You're welcome.
You did your job.
Thank you.
Okay, so we'll leave it at that for right now. I think we have a pretty decent understanding of what binary trees are. So we can kind of take that and let it stew over a break, and when we come back next Tuesday, we'll start. We'll write one of these guys. Sound good?
Yes,
Okay.
sir.
Well, everybody have a safe trip if you're traveling, or stay healthy. Don't go outside. Wear your masks. All that good jazz. I will see everybody on Tuesday. And once again, sorry we're cutting class a little short. That was a side effect of my own poor announcement the other day. I shouldn't have taken class off my calendar, because then people start filling in schedules. Okay, so I will see everybody on Tuesday. You take care.
See ya.
Easter. Salesman.
Adios.
Later.
Enjoy your Easter break.
You too.